So good afternoon, or in this case, good morning, everybody. Today I'm going to be talking a little bit about soil arching, lateral earth pressures, and what we know about K0, or the coefficient of lateral earth pressure at rest. I've prepared this talk for a class of mine which I'm taking, which is Civil 840 at Queen's University in Kingston, Ontario, and that's the class Advanced Soil Mechanics. So first and foremost, I'd like to extend my sincerest thanks to the authors whose papers make up the basis for my discussion today. I'll be presenting a brief summary of works done by McGuigan and Valsangkar 2011, Talesnick 2005, and Talesnick and Frydman 2019. I'll just go aside and note that McGuigan and Valsangkar's work was done at the University of New Brunswick, Canada, and both Talesnick 2005 and Talesnick Frydman 2019 came out of the Israeli Institute of Technology in Haifa, Israel. So please afford me just a moment before we get into today's discussion. I'd like to recap arching in soils and its impact upon the observed stress field. I know it's certainly a topic that you need an understanding of before we get too far into the meat of these three papers. So let's just examine this simple diagram which I've prepared, the case of a box culvert subject to some settlement, uniform settlement underneath an embankment height. So the first question, and probably the most important question to explore, allow me to grab my highlighter, laser pointer right there, is what would the stress be at the bottom of this box culvert? So for those of us who may already know the answer, please hold on just a moment. Let's take our engineering caps off and work our way through it in a common sense manner. So at first glance, you would probably say, well, we have some uniform settlement, we're going to have some soil of mass gamma per meter cubed, and we'll have some known height to work with, etc., etc. You might work out that overburden pressure. If you're really the type to think ahead, you might go as far to say, let's grab the concrete handbook and discern what the mass of the culvert itself acting upon itself would be, and then you might think that you're onto something. And for a common sense approach, that's actually pretty good. But we as engineering students and practicing engineers and engineering researchers, we know that these problems, they're never that simple. They always go a step or two deeper than we could imagine. So I'm going to share with you this figure from McGuigan and Valsangkar's 2011 paper, where they were taking a look at induced trench conditions and positive projecting conditions for double culverts under high embankments, as double culverts are usually preferable for water passing. So we're going to just take a look at the left case first. This is termed the positive projecting case. This could also be what we were looking at on the last slide, or the last image. So in the instance of this positive projecting case, the culvert is deemed to be much stiffer than the soil to the right and the left of it. It would be more easy to compress the soil than it would be to compress the culvert. So as these settlements take place, the soil on the right of the culvert and the soil on the left of the culvert, soil settles, more readily than the soil which directly overlays it. And so what this relative settlement does is it mobilizes these shear forces up the left and the right from the corner, projecting positively from the corner of our box culvert. So these two columns on the left and right, not the soil over top, but on the right and the left side, as they settle at an accelerated rate, they're going to try to drag that culvert soil down with them, hence the mobilized shear forces, and these frictional forces are going to actually draw load inward. So what we're going to have is a greater load than what you would expect if you'd calculated it like we did with our common sense method. So if you don't account for soil arching, which is the name of this phenomenon, you'd actually tend to underestimate, and that's a big problem, underestimating the load which would be experienced at the base of this culvert. So if you think about this concept and you flip it inside out, you can actually make it work to great effect, and that's what we'll call the induced trench setup. So in the induced trench setup, we're actually going to intentionally place some sort of compressible zone on top of the culvert, and it's going to allow this column, this load column, as we'll call it, to settle relatively faster than the soil on the right and the left. So with this expanded polystyrene, as it is in most cases, in place, If you apply equal load, it's going to be easier to compress the polystyrene than it is to compress the soil. And so what we'll have is the opposite. As this loading column directly on top of our culvert is being compressed and it's compressing more readily, the columns to the left and the columns to the right are going to resist that settlement, mobilizing shear forces upwards and hence reducing the load experienced by the culvert. So with this information in our back pocket, let's move forward to see how arching can creep its way into some of our lab research methods and therefore creep its way into our understanding of mechanics. So, a pathology of an error in research methods. Title of a paper by Mark Talesnick. So let's talk about lateral earth pressure. That's why we're here today, isn't it? So specifically the coefficient of lateral earth pressure at rest, K0. So K0 is an empirical coefficient to describe a ratio of effective horizontal stress over effective vertical stress. So it'll look something like this. Sigma H prime over sigma, we'll use Z prime, equals K0. Pardon my messy handwriting. So Talesnick and Frydman, given this is an empirical coefficient, meaning it's based upon data from laboratory tests, they set out to share concerns about the validity of this laboratory data and henceforth our understanding of K0. They were a little bit concerned about this. And so in their paper, the authors set out to determine a few things. They had a few goals going forward. They had, number one, they wanted to know what was the quality of the supporting data. Number two, what would be the outcome of the most rigorously conducted testing possible? And three, what other research areas could have been impacted by this faulty concept of K0? Were it faulty? So, the root of the problem. The development for almost all scientific theories and engineering concepts begins with an observation. And as experimental methods become more precise and comprehensive, it's our duty to revisit such observations and the data that supports them to make sure that they're correct. So error may propagate. So we should note that as theories become more advanced and concepts are built upon earlier concepts, they're only able to be as good as the original concept and the data on which it was founded. So in our case, the original issue lies within Jaccay's equation in 1948. And unfortunately, Jaccay's equation has been shown to have been based on improper assumptions about the stress state of a soil at rest, and as well an improper understanding of the conditions required to assess K0. So a handful of academics have spoken out about this improper assumption. However, to date, much of the data actually lines up with these Jaccay equation and its sibling equations, these derivative equations on the right side. So much of the data is actually in agreement with these equations, and therefore people have kind of shoved it under the bus. They don't want to think about it because it's working. But we are kind of hung up on this issue, and this leads to the topic of quite an interesting investigative paper. So as it turns out, Jaccay's equation, and therefore by association its sibling equations, were not based upon, but they were verified upon, the basis of 171 data sets from a series of experiments conducted by a plethora of reputable researchers and scientific institutions. These data sets were sourced from 5 different experimental arrangements, as you can see on the screen, and they had hopes of achieving stable and believable results. So you could only imagine if you collected 5 different data sets, well, 171 data sets, but from 5 different experimental setups, and you achieved similar or the same results 5 times, you deservedly can be quite confident in your data. So the data was collected from flexible ring odometers, rigid ring odometers, null consolidometers, triaxial tests, which we're all familiar with in Civil 840, and soil pressure transducers in pressure vessels, as pictured on the far right of your screen. So, where did the error come from? Let's talk about what it actually takes in order to be able to confidently discern and determine a value for K0. Well, Talesnick set out 3 conditions which needed to be met in order to be able to define K0 confidently in an experimental setup. So, we need a representative value for sigma z, the vertical stress. Now, do not conflate this sigma z with the vertical stress applied to the element. What we actually want is the vertical stress experienced by the element. So just think about that. There's going to be more on that later. As well, we need a representative value for sigma h, the horizontal stress experienced by the element. And we need, most difficult, a condition of zero lateral strain. It should be noted 0 is a really, really, really small number, and one which is very painful to work with in a lab setting. So Talesnick, in 2014, his paper, he demonstrated that even the most minute deflections would impact the stress field significantly, and therefore any of our assumptions or understandings of the stress state. So a review of all 171 tests found that for one reason or another, they did not satisfy all three of these prerequisite conditions for determining K0, and therefore they contributed to this erroneous working data for the parameter, erroneous working definition for the parameter. So where in these data sets did we go wrong? Where were the sources of error? Well, that changed depending on how the data was taken. Flexible ring odometers require some sort of a deflection in order to produce a stress response. And the same is true for membrane deflection in rigid ring odometers. Sidewall friction in any capacity in all of our setups impacts our ability to confidently define sigma z. So recall earlier I was talking about we can't conflate the applied load to the load experienced by the sample. Confidently define sigma z. So triaxial tests suffer from many of the issues discussed in class, specifically our ability to define sigma z. There's some issues with friction in the loading ram and where we place our load transducers, as well as sample preparation, poor seating, the list goes on. So in many applications, the deflection of the sensors induce a change in the stress field. So I've prepared a figure on the screen, not to be taken too literally, of course, see it on the bottom right here. And it just helped me at least visually understand the impacts of sensor deflection and sidewall friction upon a vertically straining element. So imagine that this is a soil sample, dark black lines representing some sort of vessel, this dotted line representing the surface, deflecting surface of a pressure transducer, and these little fletches representing sidewall friction. So subject this to a uniform settlement. What you're going to see is sidewall friction restricting the ability of the sample to settle. You're going to see increased settlement at the middle due to the pressure sensor actually deflecting and allowing it to settle more readily when compared to this infinitely stiff boundary on the left and right. So back to soil arching. What we know now with our back pocket definition of soil arching is that this is going to contribute to erroneous readings. So what's actually going to take place is as this sensor deflects, we're going to have some shear forces mobilized upwards as such that are going to resist the settlement and therefore decrease the load being registered on the sensor. So couple this with the impacts of this sidewall friction having the exact opposite effect, we're well on our way to having some interesting and messy data. So this is an example of a test which has been set up without accounting for sensor deflection or sidewall friction. We have vertical stress, sigma v, and we have horizontal stress, sigma h, plotted on the x and y axis respectively. And these are some real tests done on a pit sand. So what we actually see is some hysteresis or hysteresis depending on what part of the world you're from, but phonetics aside, hysteresis is just the dependence of a system state upon system history. And in this case, it's the believed dependence of K0, at least in the over-consolidated portion, on over-consolidation ratio to the exponent sine friction angle. So what we're looking at here is one of the most extreme cases, vertical and horizontal stress during a loading and unloading sequence. So as the sample is loaded, we see a nice linear transgression, K0 normally consolidated, Jackie's equation, sigma h over sigma z, 1 minus sine phi. That'll give you a linear plot no matter what phi is. It'll just change the slope. And then we have, okay, we've reached our peak loading, so now we're going to unload and we're in over consolidated territory. Main and Kalawi developed this relationship, and it's plotted here in the red compared to the real data. And the authors of this paper said, good enough, that's great. However, this isn't really the greatest fit, as you can see. There's a significant amount of error. Even down here you have a little reversal of the trend. It's really far from perfect. And so instead of addressing this, the authors of the paper instead just tried to explain it away and say why it was okay. So Talesnick got very hung up on the fact that we know this to be wrong. So how did it find its way into this equation? And then how did we get to here? And that's a very good question. So there has to be another explanation for this behavior. If we don't trust the Main and Calawi relationship, we don't know why it's not fitting, and we don't believe K-naught normally consolidated. I know we're starting to sound like we're denying a lot of things. But what's going on here? There has to be another explanation, and I don't claim to have a crystal ball. I've just done this presentation 6 times. But let's pretend I do have a crystal ball. I think relative settlement and sidewall friction is going to have something to do with it. So obviously I'd mentioned that this didn't sit well with Dr. Talesnick. He felt something had to be done about it. But rather than asking all of the past researchers to line up and he was going to poke holes in their methodology and have them explain, he opted to play offense. And so he asked himself, what would be the result of the most rigorous and most precise experimental setup imaginable? And if my results differ, mine being his, if his results differ, well then we'd really have something worth talking about. So let's take a look at our 2 main culprits again. Sidewall friction and sensor deflection. So how could we deal with this? Well, the first thing we're going to deal with is sensor deflection. So a soil pressure transducer, which we've seen on the past slide, is going to be installed flush within a recess in the pressure vessel so that it's a flat, flush surface. And instead of, allowing deflection to occur under loading, a system would be put in place to use air pressure, regulated air pressure, to actively preempt and stop deflections from taking place. So essentially, increasing the pressure response of the sensor in correlation with increased load to maintain a surface of 0 deflection. And from this, we are able to back calculate and use this air pressure to infer a value for applied stress. Simple, but genius. The first issue, sidewall friction, is one for which there is a much less elegant solution, but a practical one nonetheless. So by adopting a generous width to height ratio in combination with friction reduction treatment, note it's not friction elimination treatment, but merely friction reduction treatment, which is essentially 2 layers of either a polyethylene or latex membrane with some oil-based lubricant, or as recent as a few months ago, I guess, he was here in the Queen's lab, and we were using a water-based lubricant for friction treatment, and it was seen to great effect. So by adopting both a generous width to height ratio and friction treatment, we can at least minimize sidewall friction. So say we take account of both of these things, and we go back and try to reproduce this data set, how's it going to look? So let's take a look at some of the results. Let's start with Talesnick 2014, null pressure versus applied pressure. So both the null sensor and sidewall friction treatment was used in this data set, and what we had is a loose sample, air pluviated or just placed loosely, it wasn't specified, a dense sample which was placed densely or however they managed to do that, and then we applied some load and we read what load was experienced at the base. So please pardon my drawing. We have a box as such. We have a null sensor in the bottom. What we're plotting is this load applied pressure on X, and we're plotting this reading of the null sensor on Y. And what you'll note is we have a lovely Y equals X slope. So essentially every increment of load that was applied to the top of the soil is being read by the sensor at the bottom. That's really beautiful. So let's take a look at a data set from another researcher who made use of the null sensor but did not make use of friction treatment. So this is a little difficult to understand. So again, we have something like this, where we have a soil surface and some load being applied to the top, pardon me. And we have one null sensor on the right side, we have one null sensor on the left side, one null sensor on the base, B for base or bottom, and essentially these plots are x versus y1, y2, y3. So we're plotting this applied vertical stress versus each of these stress readings. The left and the right ones are pictured here in your blue and red, and this x versus y2 is plotted here. And so I'm going to leave this figure up for a second. What we see is that there's still some hysteresis. There's still a little bit of a separation between the curves during loading and unloading, even for vertical pressure versus applied pressure, which Talesnick was able to achieve an almost perfect linear line. Now, maybe we can go as far to wonder if this is because they didn't use sidewall friction treatment, and that might very well be the case. However, with just the null sensor alone, it's a significant step above the past data sets used to verify the Main-Calawi relationship. So our third figure is from Talesnick 2012, which makes use of both the null sensor and friction treatment, and it's an applied pressure versus horizontal pressure, which we should all recognize as K0. So almost linear, a little bit of hysteresis taking place, and we've tried to fit two of the following equations. We've done our best to fit K0 for the overconsolidated conditions using a fitting parameter alpha, as well as this earlier version of the same equation, the Main-Calawi relationship, where we use sine phi. So given we know the phi of this material, we were able to plot that one relatively easily up here. And as you can see, it's not the greatest fit, actually. It's quite far from it. It mimics the shape, but that's about it. And we have the other equation, number 2, using a fitting parameter alpha, although let's remember fitting parameter alpha still has to equate sine phi at the end of the day. So Talesnick says, what would I have to do in order to make this fit? He comes to a fitting parameter of 0.16, which is actually a very nice fit. However, 0.16 back calculates out to a phi which is smaller than any value that would be reasonable for the sample. So we have all of this evidence and we have all of this data, yet researchers are still managing to use the old information. And this is creeping its way into our science going forward. So what can we make of all this, and what can we learn from these experimental procedures and this rigorous testing? Well, as researchers and members of industry, we can't be fearful if our data stands alone. Unfortunately, many members of our profession, as I mentioned, are continuing to use the same old flawed approaches despite us now knowing that they're incorrect. Talesnick talks about this negative feedback loop, and I think that to be an apt description, where flawed results are used to reinforce flawed conclusions and present further flawed results to make more flawed conclusions that match the previously flawed conclusion. Anyway, it'll give you a headache if you think about it. But there's been so much interesting research done in soil mechanics which can't really be taken at face value for these reasons. It can't really be taken at face value because it hasn't considered sensor deflection or sidewall friction. The most troubling outcome of all of this is this propagation of error into some other fields of practice and research. And an example of this is the effect of compaction activities. That's obviously a super important design parameter and a super important thing to consider and have an understanding of. So if you look at the Main-Calawi relationship, it implies that there's residual impacts of compaction activities. So long after compaction loading stops, that those horizontal stresses stay jacked up. But to what degree is that true? Well, unfortunately, it's hard to tell, and we don't really know, because some of the major studies on the topic have failed to account for sensor deflection and especially sidewall friction. And so researchers not accounting for some of these factors have led to some erroneous conclusions. So I think if there's going to be a take-home point from today's talk, I know we had to wrap things up a little bit quickly, it's that we as a profession and engineering students need to be ready and willing to accept fault. If new and rigorous observations aren't able to find a place within the body of literature simply because they stand alone, we're going to stunt the development of our field of science. I think many of us researchers could use a reminder that we're not only trying to prove ourselves right, but that we must also be open to being proven wrong. Thank you very much.